Welcome to another video in the Physics Advanced series of videos. Today I will be talking to you about accuracy and precision. When we deal with measurements in science, there's a certain amount of uncertainty involved with those measurements. We have two ways of describing that uncertainty. We can talk about that uncertainty in terms of accuracy as well as precision. These two terms imply different things, and it's important to understand the difference between those two terms. When we talk about accuracy, what we're really talking about is the ability to achieve or measure the true value. So again, accuracy refers to the closeness of a given measurement to its true value. Precision, when we talk about precision, we're talking about the ability to make a measurement and repeat that measurement multiple times, over and over and over again. Your accuracy is essentially related to the instrument that you're using, whether it's a good instrument for getting the kind of data you want, or whether it's just a rough approximation. Whereas your precision, although it's also related to your instrument, is also related to your methodology that you use as well. When we work in science, we want to be able to express some of that precision when we take down our data. We're always looking to be as accurate as we can. We're hoping that the device we're using is trying to give us an accurate measurement of what it is that we are manipulating. But we also need to think about, if we were to measure this again, what would we get? So here, for instance, you can see an example of, let's say if you measured a man, you found him to be 6.01, 6.02, 5.99 feet. In each of these cases, there's a certain amount of uncertainty. And really, when we make measurements, we generally think that the last number in our data is essentially somewhat uncertain. It could be a little higher or a little lower. So when you see numbers like this, 6.0100 or 6.0201 or so on and so on, what this is really showing is that these measurements are more precise than these measurements. In other words, if I were to make these measurements several times, for instance, you would more likely get that same measurement multiple times, whereas these, you're going to see that variation is going to change that number a little bit more drastically. And again, part of that has to do with the precision. So we use significant figures to represent precision. And so in our next portion, we're going to talk a little bit more about that. Alright, so if you remember, we're talking about significant figures, how significant figures represent precision. The precision of a measurement is essentially the ability to repeat that measurement multiple times. This little diagram is going to also help illustrate the difference between accuracy and precision, and then we're going to talk a little bit more about significant figures. So we've got this picture down here, and you've got these targets. You can imagine that the bullseye is essentially the true value, the actual value of the measurement, whatever it may be. And then each of these yellow dots essentially represents a measurement that you might make. So if you were to look at this picture, for instance, if you look here, you see something that is, well, it's accurate because it's hitting the bullseye. It's actually making the correct measurement and is actually fairly repeatable. You can see that we've done it multiple times, and essentially we're getting that clustering, and so all of our data points are sort of in the same place. So this is a picture diagram, something that is accurate and precise. Over here, we have something where the data points are clustered, so they're precise, but you'll notice that none of them actually get the true value. So this data set would be precise, but not accurate. This data set is not as precise. You can see it's spread out. There's several data points here and there, but if we did take the average of these points, we would see that essentially we'd have something that was close to the bullseye. So this is an example of something that is not precise, but it is accurate. So in terms of the question, is it possible to be precise but not accurate? The answer is yes. And if you go back and look at those three diagrams we just talked about, one of them, again, was is it possibly precise but not accurate? So one of those did show that it is possible to be precise but not accurate. And for those of you still wondering which one that is, again, so be precise but not accurate would be, again, precise but not accurate would be C. Alright, so significant figures, which we use to represent how precise a measurement is. Sometimes you're going to see data or results, and you're not going to know what was used to measure that particular measurement, and you need to decide, okay, how precise is this compared to another number? And so what you want to do is figure out how many significant figures you have. So we're going to go over the rules for figuring out how many significant figures a measurement has. Something I should point out before I go any further is that in the end, your number of significant figures is really based on the measuring tool that you're using. For instance, if we're talking about a meter stick, right? A meter stick is going to be able to measure meters, then decimeters, then centimeters. It probably has millimeter marks on it as well, and to some extent you can approximate roughly the space between the millimeter marks. So that's actually accurate down to, that would be 1.0 for the deci, 0 for the centi, 0 for the milli, and you might be able to approximate one more. So you're essentially looking at 1.0000 meters if you were to actually measure a true meter using that meter stick, which means that essentially you'd actually be working with 5 significant figures. Okay, so that's one of the reasons we use meter sticks. They're relatively accurate. And even if you want to quibble about the last space, you still got at least 4 significant figures there. Alright, now, if we were to have a number, though, just in front of us, and we didn't know what was used to measure it, we might need to figure out how many significant figures it has. So, here are the rules. For a given number, the rules are everything that is not 0 is significant. Anything that is furthest to the right of the decimal, no matter what it is, even if it's a 0, is significant. And all digits that lie between significant figures, no matter how many there are, all digits that lie between significant figures are also significant. Those 3 rules will help you determine how many significant figures any normal number that you write down might have. It gets a lot easier for scientific notation in that in scientific notation all you have to do is look at basically the portion called the significand, and if you look there, for instance, like here, 2.0 times 10 to the second, the 2.0 is the significand, so this has 2 significant figures. Over here, this is 2.00 times 10 to the second, so this has 3 significant figures. In other words, for scientific notation, all you have to do is just count the number of digits, zeros or not zeros, that are being shown in the significand. If you're writing good scientific notation, then you should remember you should only have one number in front of the decimal. Okay, that's the standard accepted practice. Another thing to keep in mind, some things are infinitely significant. For instance, counts. Counts are infinitely significant. For instance, if we were talking about a herd of zebra and there were 90 zebras, well, there's 90 zebras or there's not 90 zebras. There's not 90.5 zebras or 89.5 zebras. That'd be gory. So you for counts, you can basically just say that it's infinitely significant. So for instance, normally if I were to look at 90, I might say, oh, its significant value is it's 1. We'll go through the rules on that one again in just a moment. But in this case, if it was a count like 90 zebras, it would be just purely 90. Now again, you'll notice I said that this 90 right here is infinitely significant. If it were like 90 meters, it would be a number that has only one significant figure, because the first number is significant because it's not a 0. However, there are no numbers to the right of the decimal, and this 0 is not between any significant figures. So according to the first rule, that's the only one that applies. It has one significant figure, and that would be that. Okay, so we're going to run through the significant figure rules with these examples. We're going to assume that essentially all of these numbers are some type of measurement. Let's just say that every single one of these is in grams. So none of these are counts, so none of them are infinitely significant, although probably the only one that could be infinitely significant would be the first one, because the first one is 15, and 15 is a whole number, so you could have a count of 15. I guess 150 as well would be another option. But again, we're going to go ahead and just say that, for instance, it's 15 grams and 1.5 grams and so on and so on. And so we're going to look at how many significant figures each of these has, talk a little bit about why, and remember that our significant figures are basically describing how precise this measurement is. So first one, 1 is a non-zero number, 5 is a non-zero number. That means we are going to have 2 significant figures. Second one, 1 is a non-zero number, 5 is a non-zero number, 2 significant figures. 150, 1 is a non-zero number, 5 is a non-zero number, 0 is a 0, and that's unless it's to the furthest to the right of the decimal or between things, it's not going to be significant. So actually 150 also only has 2 significant figures. 0.15, okay, so the 5 is significant, the 1 is significant, but the 0 before the decimal is not furthest to the right, and it's not between any numbers that are significant. So actually this also has 2 significant figures. 1.05, you'll notice the 1 is significant, the 5 is significant, but now the 0 is also significant because the 0 lies between 2 significant figures. Again, these 2 being 5 and 1. So we have 3 significant figures in that one. The next one, 15.0015. The 5 furthest to the right is significant. All the non-zeros are significant, and you've got 2 zeros that are lying between significant figures. In this case, 5 is significant, 1 is significant, which means that those zeros become significant as well. So actually, all the numbers in this particular number are significant. So we would say that it actually has 6 significant figures. For the next one, 5 is significant, 1 is significant. None of the zeros, though, lie between significant figures, nor are they furthest to the right. So 2 significant figures. 0.105, 3 significant figures. 15.00, notice the 0 is furthest to the right. The 5 is significant, so that makes the other 0 significant as well, because it now lies between the 0 that is furthest to the right, as well as 5. So that's 4 significant figures. We've got 2 more. The next one, there's 0.001 grams. None of the zeros are between any significant figures. None of the zeros are furthest to the right. So the only significant figure is the 1. So it's got 1 significant figure. And then this last one, 0.150. The 1 is significant. The 5 is significant. The 0 is furthest to the right, so it is also significant. The 0 before the point, however, or the 0 before the decimal if you prefer, is not significant. It does not fall into any of those rules. So consequently, we've got 3 significant figures. And there you go. That's significant figures.